Today we're going to talk about collision theory and energy diagrams. We're going to start by looking at a video, just the first part of the video, about how to speed up a chemical reaction and get a date.
When I'm on the go, it's often much easier for me to just send a quick audio clip or video clip to the team rather than having to type out a long message. Sponsors are on board for next year. Let's get the ball rolling.
Get 50% off Slack Pro, a more simple way to work.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it.
So let's talk about effective collisions. In order for reactions to occur, you must have collisions. Now, it cannot just be any type of collisions. There has to be 2 things. You have to have sufficient energy and you have to have correct orientation. So the picture I have up here is of a fender bender where there's a car accident. You can see there's a dent in the car. And so you have correct orientation, but this is minor. There's not much damage. There is not sufficient energy. So this would not be what we would consider an effective collision. This next picture I have, you can see a lot more damage is done. We have sufficient energy. You can see the airbag has been deployed, so there's sufficient energy in this collision and correct orientation. So this would be what we would call a effective collision. So 2 particles must collide with correct orientation and sufficient energy to break bonds. And so we're going to look at 3 different collisions and and talk about why they are favorable or not favorable. So we have the collision between particles AB to form, we have the reaction of AB And so if you look at letter A, we have an effective collision. It's favorable orientation, sufficient energy, so reactants form products. In the center, you have them oriented correctly, but the collision is too gentle. So you're just going to have them rebound without forming products. And then at the end, collision has poor orientation. There's no reaction. No products aren't formed either. So the only way that you're going to have an effective collision is if you have favorable orientation and sufficient energy. If we look at this in terms of an actual reaction with hydrogen iodide molecules colliding, the only way that products are formed is if you have this orientation on the left right here. This is the only orientation that would result in the formation of products. Any of the other orientations on the right will not form products. You still have to have sufficient energy also, but you have to have the correct energy. So now that we know the requirements for an effective collision in order for reactants to produce products, we're going to look at some energy diagrams. So we're going to start off with the exothermic energy diagram. An exothermic energy diagram, the energy of the products is lower. And I'm going to give you a moment to draw this energy diagram, and then we're going to label it. On the left-hand side are always your reactants. On the right-hand side are your products. And then in the middle is your activated complex. And so we know what reactants and products are. Let's define activated complex. This is a transitional structure that results from an effective collision and persists while old bonds are breaking and new bonds are forming. This E sub A in the middle is activation energy. And activation energy is defined as the minimum energy required to transform reactants into the activated complex. So you should be able to draw an exothermic energy diagram. It should make sense that the energy of the products is lower than the reactants, because if it's exothermic, energy is released. We can also draw an endothermic energy diagram, and so we'll do that next, and we'll label it. And so an endothermic energy diagram, the energy of the products is higher. Than the reactants. And this should make sense because we know endothermic means energy is absorbed. So I want you to draw this energy diagram, and then we'll label it. And so reactants are always on the left. Products are always on the right. In the middle, at the top of the activation energy, is your activated complex. And then E sub A, this arrow here, is your activation energy. So you should be able to identify, given an energy diagram, you should be able to identify if it's exothermic or endothermic. You should be able to identify the reactants, the products, the activated complex. If you were given data, you should be able to draw an energy diagram.